Hi, my name is Manuel, and today I want to show you how we use the graph network to enhance neighborhood operations in a landslide detection pipeline. The pipeline consists of three major steps. For a better understanding, I want to quickly describe the whole framework and its goals before talking about the advantages of the graph network in more detail. A strong focus of our work lies on the simple application of this approach for various regions. To make it available for a vast range of users, we chose to work with open data and free software. The first step of the framework is the data collection and pre-processing. This is done using Python API of the Alaska Satellite Facility Vortex for Sentinel-1 data and the Google Earth Engine API for Sentinel-2 elevation and land cover data. All processing steps are done using Python in combination with the Google Earth Engine, the Snappy library, and GDAL. After the processing and stacking of all input data, the second step is the graph creation. We use the elevation data to create nodes and connect these with edges according to the flow direction. Neighborhood operations describing the topology of each pixel can then be carried out along the edges of the graph network. In the last step, we use all the information about the pixel itself and its surrounding to run an individual random forest classifier on each node for each land cover surface. For the first application of the pipeline, we chose the Weheka Valley, which is located on the west coast of New Zealand's South Island. During the year 2018, a landslide continuously grew from 30 to around 500 meters width at its widest point. As data, we use pre- and past-event Sentinel-1 composites and Sentinel-1 beta-node products, which we calculate the change. Furthermore, we use SRPM1 arcsecond product for the digital elevation model and land cover data of the year 2017. So back to the importance of neighborhood for machine learning. Neighborhood operations are used to integrate the surroundings of a pixel in a classification process. A good example is the difference between coniferous and deciduous woodlands. While one pixel alone gives no clear indication on the tree type, a smooth neighborhood is a good indication for a deciduous forest. A common method to determine the neighborhood is the use of a weighted n×n moving window. The weights in the window can be used to highlight specific geometries. However, landslides do not follow these specific geometries. The shape is based on the topography of the area. So how do we integrate the topography? We decided to use a graph network which consists of nodes for each pixel using the elevation of the SRPM product in combination with pixels northing and easting coordinates. Between the neighboring nodes, we calculate the slope in all directions. The nodes with the steepest angle are then connected with the edge. This connection is stored in an edge list, which can be used to recursively determine all pixels up and down the slope of our node for a given distance. While running a mean filter with a common moving window approach blurs small objects or the borders of larger ones, the mean calculated from the graph network keeps the shape similar to the original data. Furthermore, one can differentiate between downslope, upslope, and combined statistics. While the effect is especially important for small-scale events, one can still recognize the difference in the foot of this large landslide, where the slide avoids some smaller humps. So what next? First, we want to train the random forest on more land covers and integrate other data products. And second, we want to look at different methods to simulate the flow. And with this, I'm at the end of my presentation and want to thank you for your time, and I'm happy to answer any questions.